I will continue the series with 3 very well-known problems. The first problem I want to cover is the knapsack problem. So in this problem, we are given n items with integer weights and values. Say kilograms and dollars, and we have a budget also integer. Okay. The goal is to pick a subset of items whose total weight does not exceed k, that maximizes the total value. So basically, you're trying to pick a subset of these n items to maximize the value that you can get, with the constraint that their total weight does not exceed k kilograms. Okay, so all 3 quantities, the weights, the values, and the budget are integers. Okay, so we can let the weights be stored in the vector w, and the values be stored in the vector v. So how do we solve this problem? Let me define the subproblem. So one thing I forgot to mention is that the weight as strictly positive, and also for simplicity we can think of the values to be, say, greater than 0, because if the values are 0 or negative, you might just throw them away. So let's define the subproblem. Let bpij be the maximum value we can get from items 1 up to I with a budget j. Alright, so this is a subproblem in the sense that instead of looking at all n items, you might look at just the first I items, and instead of having a budget K, you might look at a smaller budget K, J. So how do we solve this problem? Let's look at the easy base cases. For I 0, 1, 2 up to n, it is fairly easy to see that dp of I0 is 0, right? Because if all the weights are positive and you have 0 budget, then clearly you cannot carry any item. So you get 0 value. For j from 0, 1, 2 up to k, dp 0j is also 0. It doesn't matter how much budget you have. If you have 0 items to choose from, then clearly you get nothing but 0 value. Okay, so these are the base cases. Okay, so now let's build the dynamic programming table. For I from 1, 2 up to n, and for j from 1, 2 up to k. This is what I'm going to do. If the weight of item I, right, is strictly larger than j, then clearly you cannot fit. Okay, so you are trying to see what's the best you can get out of the first I items with a budget j. But now the I item has weight more than j, right? So you cannot really carry it anyway, right? So dp ij is just equal to dp of I minus 1j. Okay, so this case is fairly easy. Now, otherwise, if item I can fit within the budget j, right? So there are two cases. Either you pick item I in the optimal solution, or you don't. Right? So dpij is the following, right? So if you pick item I, right, what you get is the value of item I plus the most that you can get from item 1 to I minus 1. But because you pick item I, you have now your budget is j subtract the weight of item I. Okay, so this is, if we select item I, this is the best that we can get. We get the value of item I plus the most value we can get from item 1 up to I minus 1, restricted to a smaller weight j minus wi. Okay, so now the other case, if you don't pick item I, what's the best you can get? We'll get, now we still have items 1 to I minus 1 to choose from, and we still have the entire budget to use j, right? So the optimal solution is either selects item I or it doesn't, right? So we simply take the maximum between the two, and that's it, right? So at the end we just return dp of nk and we are done. Alright, so that's the first problem. Next we look at another very similar problem called the subset sum problem. In this problem we are given an input that is an array A that contains n positive integers, and a target number t also integer, otherwise it is trivial. So the goal is to decide, you can think of, output true or false. If there is a subset of A that sum to T. Okay, so you can think of A as a multiset, and you ask if there is a subset of integers of A that sum to T. Alright, so this problem is very similar to the previous problem. Let dp ij be true if there is a subset of elements of the first I number of A that sum to J and false. Otherwise, if there's no such subset, output false. Okay, so we can make the base case that dp0 0 is true. This is somewhat difficult to pinpoint exactly, but you can think of the sum of the empty subset is 0. Right? Now, for j from 1 to up to t, we have dp of 0j is obviously false. Because an empty subset doesn't contain any, an empty set does not contain any subset whose elements sum to a positive number. That's all it means. All right, so for I from 1 to up to n, and for j from 1 to up to t. Okay, now if ai is strictly larger than t, then clearly, right, ai cannot belong to the subset if there is one that sums to t. So dp I j is equal to dp of I minus 1j. Okay, again, if ai is larger than t, that means that if there exists a subset of the first I items that sum to t, then clearly that subset cannot contain ai, right? Because we assume all elements are positive, and ai is already strictly larger than t, so you cannot have ai in that subset. Now, otherwise, you can either include ai or you may ignore it, right? So you can say, well, dp of ij is equal to, well, if you include ai, right, that means you must be able to find a subset of the first I minus 1 numbers that sum to j minus ai. if you this is an OR. Now, if you do not include AI, right, then there must be a subset of the first I minus 1 element that sum to J. So again, so in order for a subset of the first I numbers, in order to have a subset of the first I number that sum to J, there must be one of the following, at least one of the following cases must be true. There is a subset of the first I minus 1 numbers whose sum is J minus AI, and then you put AI into that set. Now you have a subset whose sum is J. Or, if there is a subset of the first I minus 1 numbers whose sum is J. So that's it. Very similar to an abstract problem. And so at the end, all you have to do is just return dp of n and t. Okay, so then we are done with the second problem. The final problem that I will look at in this video is the longest palindromic subsequence. Problem. Probably you know what a palindrome is, but I will define it here. A palindrome is a string that is the same as its inverse. For example, race car or tenet. So in this problem, the input is just a string A, and you want to output the length of the longest palindromic subsequence of A. Let's look at a concrete example. Subsequence of A. Let's look at a concrete example. Example. Let's say A is the following string: A R A C A B ERCK AB. Right. So in this example, you can sort of check that the longest palindromic subsequence is I forgot an R at the end. I'm sorry, this B should be yeah, so as probably you can guess, the longest palindromic subsequence here is raise car. Right. So the output should be 7. Okay, so I hope the problem is clear. So how do we define the subproblem? Let dpij be the length of the longest palindromic subsequence of somewhere between AI and AJ. Consider this subarray AI and AJ, and you want to find the longest palindromic subsequence of this subarray. Clearly, it's a subproblem. So let us look at the base cases. dp of 0, 0, I'm sorry, dp of I is equal to 1, right? Because the longest palindromic subsequence of a single letter is itself. Now, dp of ij is 0 if I is larger than j, because the subarray between AI to AJ, if I is larger than j, is an empty subarray, right? So these are obvious. Okay, so you can do the following. Well, for I from 1 to n, I from 1 to n, dpii is 0 for I from 1 up to n. For j from 1 up to I minus 1. Say, well, dpij is 0. So these are the base cases. Now, to fill up this dynamic programming table, we need to be more careful compared to what we did in the past. Well, here's the idea. Right? So let's look at the substring AI plus 1 up to aj minus 1 and aj. There are three cases. If AI is equal to aj, okay, okay, so if AI is not the same as aj, right, then the longest palindromic subsequence of AI to aj must exclude either AI or aj. The longest palindromic subsequence of AI to aj must exclude either AI or aj. Right. So in this case, if AI is not equal to aj, what we'll have is that dpij is equal to dp of is equal to the larger value between dpi plus 1j or dp of I j minus 1. Okay, so let's look at the other case where if AI is equal to aj, right? The simplest thing we can do is, okay, so the longest palindromic subsequence might include both AI and aj, right? And that's certainly the option. So dpij is the maximum between these three cases. So dp of I plus 1, j minus 1, plus 2. Or you can ignore ai plus 1 or aj minus 1. Well, some of these cases are redundant, but that's okay. It won't affect the running time. So this is the recursive structure. This is how we are going to fill out the dynamic programming table. For t from 1 to ... up to n-1. For I from 1 to ... up to n-t. What we can do is the following. So if AI is different than AI plus t, then dp of I plus t as we mentioned is the ledger between dp of I plus 1, I plus t minus 1, and dp of I and I plus t minus 1 versus I plus 1 comma t. Otherwise, dp of I plus t is the largest among dp of I plus 1, I plus t minus 1 plus 2, or I comma I plus t minus 1 on dp of I plus 1, I plus t. Right. So at the end we just okay, so originally we can say, well, let's max v1 if dp of I plus t is larger than max, we can update max, right? And at the end we can just return max. Okay. So the reason this dp or this approach works is that when you try to compute dp I and I plus t, you look at dp of the way we are thinking about this problem is, okay, so we are trying to solve a problem, subproblem of size t. That means I comma I plus t, right? Then we are looking at subproblem of smaller size, right? I plus t minus 1 or I plus 1 t, or I plus 1, I plus 1, I plus t minus 1, right? So these are the three smaller subproblems that have been computed in previous iterations. All right, so I think that concludes this video. I will see you in other ones. Goodbye for now.